very much, Hussein and ITAMP, and all of you. You don't know me yet because I just arrived in the middle of the snowstorm in a little tiny car. I'd like to welcome you all, though, to the Thursday evening of the Zoosh. Skiing after down to the. I'm one of the, like many of the lecturers, not exclusively the only one. I'm one of the old timers in strong field ionization, and although I've been working along with Linda Young and many other people in the strong field X-ray part of this for a while, I thought that in my first lecture would be a really good idea to pull back and go to when Tony Starris and Paul and all of us were kids, and we were first getting this. So I will say a little bit about that in this first lecture. Strong field photoionization, that is before high harmonics. What can we learn from all the electrons that don't end up making high harmonics or attosecond pulses? So that's the first lecture. I'll return to X-rays in lecture 2. Lecture 2 for me is going to be on X-ray free electron laser basics. That is what's inside the box. Those of us who are experimentalists always like to know what's inside our laser box. And lecture 3 will be on the thing that's closest to my current research, which is transient impulsive X-ray methods, which we think is a path to realize molecular movies in a somewhat different approach than the other areas of attosecond. Okay, so you won't get to meet up with any of these guys, but they all helped me not only with this presentation but all of my research. So here's my group, probably the strongest group that I've ever had. I have right now. And then also, I assume all this stuff gets posted, and I have a few really general references that do dig down into the background a little bit more. And also want to acknowledge Lou DeMauro, Marcus Gurr, and Adi Natan especially for helping with some of these slides. So let's get to it. So this is by now such a familiar and iconic picture for all of you. You know what this is. You draw a little funnel and you say, that's not a funnel, that's a Coulomb potential. I know that. And you draw a little wiggle and say, that's not a wiggle, that's a bound electron. Okay, I know that too. And this is tunnel ionization. Now, what you probably also have heard, but maybe it wasn't emphasized too much, is that there's a static model prediction here for when the ionization should happen independent of quantum mechanics. And that is that this electron, just by the fact that one of the walls of its confining potential goes away in a strong field, it will ionize, and the critical field for that in atomic units, which of course we are all using atomic units in this lecture. Atomic units, yes. And atomic units is just the square of the ionization potential divided by 4. That's the static model prediction. Now, in the early days, this prediction was tested. It's easy to test. You just try it out with a lot of atoms that have different ionization potentials. And it looked like this. It was just a shockingly accurate estimate, particularly if you put it on log-log scales where there's 4 decades on each axis, that you hide lots of sins. But look at all of these. These are basically all the rare gases plus their readily accessible ionization stages. And they all hang out in their ground states until you get to some critical field which is given by this formula, and they ionize. This was first noticed way back in 1989 by Steve Ochs at the University of Rochester and a bunch of other people. I think Meyerhofer definitely down the street like this around. Okay, so that's static, but the field we're applying isn't static. So what happens after? Now we get to the stuff that I'm sure Paul and everybody else covered, the ponderomotive energy of a free electron, which is addressing the continuum. So here's, again, it's not a wiggly line, it's an oscillating electric field. We all know that by now. And classical physics tells us that the energy of the electron in this wiggling is the ponderomotive potential energy that scales like the square of the electric field in scales like the inverse square of the driving frequency, meaning it's a very, very big deal for microwaves, a super big deal. And that's what all this physics comes from. It comes actually from this word Ponder motive. It comes from people who studied inverse Bremsstrahlung and low-density plasmas driven by microwaves. That's where it comes from. And actually, I think, Paul, maybe you even come from that background too. Okay, so I don't. I'm a laser jock through it, but I know about this because in those early days, we realized that was a big scaling. 1 electron volt worth of kinetic energy at 800 nanometer laser light for about 2 times 10 to the 13 watts per square centimeter, very easy to get to. Now, the thing I want to point out with respect to photoionization spectroscopy, which maybe hasn't been talked about too much yet, is that this Ponder motive energy is not quantized. It can be greater than or less than the quantum of the electromagnetic field, and it's big compared to that. It's big compared to that, or at least on the same scale. So it should dominate. Quantization shouldn't dominate. It should dominate. You would think. One would think. Let's see how that affects the ionization process. Okay. Well, first we might want to make sure that we're not completely leaving quantum mechanics behind. So there's quantum treatment. Perhaps this has also been alluded to, but this is much more important for the photoionization of the electrons. Well, I'll go over it a little bit. This is particular treatment that I'm talking about is due to Amos. I may have not even spelled those names right. I was writing this in such a hurry, but I think Amos, Deloney, and Kranoff are spelled correctly. They said that let's not think of this as a classical process. Let's think of this as a quantum tunneling process. We have an approximately wedge-shaped barrier that our electron has to tunnel through. Real easy to calculate it if we even approximate it as a wedge. And we get some formula. That's a static field formula for the tunnel current. And from that you get a tunnel decay rate, a decay constant. However, we know that this is in the process of changing all the time. It's oscillating back and forth, but it's oscillating very slow. So at any given instant, it's kind of static, but we have to integrate over that time. That's the idea. That's the whole calculation that they did. The rest is just, left as a homework problem if you really want to redo it. And you get that that the result, the rate for ionization, then should scale like all the things it should scale at. First, the shape of the potential. So there's a z dependence. Also, it's how big the field is. So there's a field dependence. That's what the square root of I is. There's a question about how deeply bound the electron is. That's what n star is. It's the effective, assuming a hydrogenic model, it's the effective quantum number of the binding energy of the electron. Sometimes called the effective quantum number. And then there's a couple of other sets of constants. D is just dependent on those same quantities. Okay, so you get that, and what you find if you try to ionize using this formula is that it works pretty well. Well, so did the static field formula. So they're not that terribly at odds with each other. And a characteristic ratio of timescales comes out, which is exactly the one you'd imagine needs to be dealt with. And that is, what wins, the tunnel rate or the oscillation of the field? So in one cycle, do you get everything out, or you only get a little out, you got to wait for the field to turn around again. That ratio is characterized by this parameter gamma, the Keldysh parameter, which can be put in terms of the ionization energy and the Ponder motive potential. And if the Keldysh parameter is 1, that means you have equality for those rates. So if it's smaller than 1, then you're in the tunnel regime, where tunneling is fast, and if it's larger than 1, tunneling is slow, compared to that characteristic cycle. Okay, that's enough hand waving. Let's let the computer wave its hand a little bit and take a look at what the classical prediction is for the drift of an electron if it's created at a particular time during a laser pulse. So here is a laser pulse. This is the trajectory of the electron, classical trajectory. The rule is that it's created at zero velocity, and this is this is time, this is distance from the atom. So you can see it sailing away from the atom up, or on the other half cycle it will come down. And you also see that on the way out it gets a few wiggles. Okay. The drift energy clearly depends on when the ionization happens during the pulse. Let's see if I can move on here. Okay. So following the ionization, acceleration in the field leads to that drift energy. So here again is that oscillating field, sine omega t electric field. Okay? And the ionization happens at some instant during that cycle. And I can characterize the time simply by a phase. It's the phase during one cycle. Presumably this could happen on any cycle, and will happen again on the next cycle. But let's just consider this phase as the sort of surrogate for the time in units of radians of the electric field cycle. At that time, this tunneling or over the barrel, whatever happens, and you create an electron with zero velocity. And then it sails, and you saw its trajectory in that classical simulation. Now, if this time is 4 degrees past the peak, then here's what the trajectory looks like. And you end up, after the pulse has gone by, with an electron that's sailing off in this negative direction with a certain velocity. Well, what happens if I move this a very tiny amount? Let's go from 4 degrees past peak to 8 degrees. It has a huge effect on the drift energy. So the drift energy is extremely sensitive to the time of ionization. So remember that when we start talking about the spectrum. We're going to see some fast electrons, and we're going to see some slow electrons. And we now have a model, albeit a crummy classical model, but look how well it works in things like the total ionization rate. Not bad, right? Right, Ken? Not bad. Not bad. So, it says 4 degrees past, 8 degrees past, that determines, that tiny amount determines that energy. So we'll think about that. All right. By the way, it's just a classical formula, that dependence of the final velocity on the phase. And so I just wrote it out. This is assuming that you start out with zero velocity when you ionize. You could question that assumption too. Okay. So, now, electrons are quantum mechanical objects, right? Starter thinks they are. And that means that I have to worry about which path type stuff and add up paths, right, that result in the same final state. So in this case, the final state is an electron with a certain velocity. So here are some electrons that I tried to catch when they exited with the same velocity, but they were clearly produced at different times. In fact, electrons with the same energy are made many times over a laser pulse. We were just discussing this, in fact. How many times are they made per cycle? How many times is this velocity made per one cycle? Hands? Come on.
Twice.
Twice. Twice. Roughly speaking, once when the electron just goes out in always feeling the force in the direction that pulls it in its ultimate direction of its ultimate velocity, and once when it actually started the other way and turned around. Twice per cycle, cycle after cycle after cycle, it all adds up coherently. What should we expect? If the trajectories are constructive, then the electron current is enhanced. And so we expect periodic maxima in the photoelectron spectrum, and we see it. Okay? The earliest, well, I got to say that Pierre Agostini, who actually did see this first, didn't have very good data. But within a couple of years, there was great data like this that showed that, yeah, this really, yeah, here, this constructive interference of trajectories, man, electrons are really quantum mechanical. This is really great. Oh, cool. Right. You know, it's really, really tempting to forget about all this classical ionization stuff now and say, no, that's just a multiphoton process. Look, it's a multiphoton process, right? I can line up the arrowheads of multiple photons that start from the ground state, zoom right past the ionization potential after 1, 2, 3, 4, 5, 6 photons, and keep on going. And it's really tempting to show that. I succumbed to that temptation myself back in my youth. It's actually misleading. That's what people say when, what was it that Pauli said? Correct me if I'm wrong, I think it was Pauli who said, that isn't even wrong. So it has that aspect. It's misleading. Okay, here's another one. This happens to be in xenon. And it was made with a typical intense laser of the day being 30 years ago, around a 30 picosecond long pulse, 1 micron, so it was probably neodymium doped YAG laser, focused to about 30 terawatts per square centimeter. This magical 10 to the 13 coming right in. That's exactly what we would expect. See this beautiful ATI spectrum, and I think my first clip will show, yep, they match right up. They match right up. They match right up. What about all that ponderomotive energy, though? Well, one way to think about that, since the spacing is 1 photon, and the angular distributions are also consistent with perturbation theory, one way to think about that is that it really is multiphoton, except the atom is strongly affected by the field, by this sort of oscillating field. Its bound states acquire this need to wiggle. They get distorted. And that distortion raises the ionization potential so that it takes more work to go from the ground state of xenon, where the electrons are all tightly bound, to anywhere near this ionization potential where one of the electrons is like a free electron, it's very loosely bound. So what that suggests is that it just takes more work to ionize the atom. And the amount of extra work that it takes, assuming that not much is happening to the tightly bound ground state. Let's see, trying to think of the Pan, Eberle, and Armstrong, right? Those were the 3 theorists who demonstrated that nothing much should be going on with this ground state back in the old days in a very simple, elegant way. So this picture they were very much in favor of. They reinforced the idea that it just takes more energy to ionize, but then it's really just multiphoton. And that predicts that these low peaks you shouldn't see because they're round. You know, they don't produce electrons, and sure enough, it is suppressed. It is suppressed. The trouble is, if those bound states are acquiring extra energy, then what about all these electrons? Aren't they acquiring extra energy too? And how come I don't see that wiggle energy has to be added in or subtracted off from the drift? Subtracted off, I guess, would be the right thing, from the drift. And so why isn't it smear everything out? Why not? Okay, well, actually people figured it out. The reason is that this ponderomotive energy, this wiggle energy, actually acts like an effective potential energy in a time-averaged Hamiltonian sense. So my electrons, once freed, once they're several angstroms away from their paired ion, they ain't coming back no more. They will get to my detector. But on the way to the detector, they have to get out of the laser focus. So this is the focus of my laser, a much more macroscopic object than just the field of the Coulomb field of an atom. These free electrons might have been produced from an atom here, or here, or here. And if they were produced here, they were produced with a lot of wiggle energy, here with just a little. But they have to get out of that ponderomotive potential. And that skiing out, if only we had If only we were at Les Ouches. There are all kinds of puns I could make here. That departure of the electrons from a more or less static, not changing very fast, ski slope converts their wiggle energy efficiently through just conservation of energy into drift energy. And so we see the electrons with all of their energy converted into drift, even though we know that we made them with a lot of wiggle and a little drift. That's the idea. So the Pomerode ski run, how long does it take? Back of the envelope will tell you that it takes a few picoseconds for the kind of ways we can focus a laser. Now, how many of you are, or at least are in an aspirational way, if not actually professional at the moment, how many of you are theorists? I should have asked it the other way around. How many of you are experimentalists? Ah, okay, well I shouldn't be talking to you folks. Well, you know how well you can focus a laser beam? Probably. Do you know how well you can focus a laser beam? Yeah. Excuse me?
What do you mean?
Well, how small is this wave? That would be really good. It's bigger because it's practical stuff. There's a vacuum chamber about this big, and I have a few millijoules that I'm trying to focus it to only tens of terawatts per square centimeter and stuff like that. Anyway, you put all those numbers in, and it turns out that this is many tens of microns across, maybe even 100. 100 would be big, but it wouldn't be crazy. And so it takes some time. It takes several picoseconds for the electrons to get out. So it's a good thing, it's a darn good thing that we were back in the Stone Ages and only had tens or 100 picosecond lasers so we could see all that physics. Otherwise, we would have just missed it. Okay? Well, 1990 comes along and ultra-fast science starts to embrace femtosecond technology. And we know that in a femtosecond, these electrons hardly move. So all that quantum mode of energy should just vanish. You won't be able to convert it into drift energy anymore. So I'll get to that in a second. So I wanted to summarize. I wanted to go even slower. I hope you're not sleepy yet, but I'm trying to go so slow. What I do is as I get this sort of pattern going, I start telling jokes and I look at people. It's a way of going slow. You may have noticed this if you teach. You notice it. Anyway, what have we learned so far? Well, we've learned that in this oscillating field, ionization happens at a rate that depends on the distortion of the field, maximum ionization up top, and that the escape velocity depends on where it was ionized to, maximum escape velocity down low. We learned that. We also learned that this above-threshold ionization spectrum is actually a little bit complicated. First of all, it's all displaced by the Pomerode potential. You can see that from the channel suppression. We learned that. We also learned that some kind of tunneling or ADK idea controls how these pulses are dropping off faster and faster and faster, and that you more or less don't see much going on anymore after the most energetic electrons, which happen about, if they were ionized right at the zero crossing, you'd have to worry about how that happens. Then they would come out at an energy of 3 UP. That's 2 Pomerode potential units for the shape of this curve, and 1 because of this displacement. We learned all that. We've learned all that. Now we go to short pulses. Short pulses, which again came in the early 90s, they should suppress, late 80s, early 90s, it's all the same, should suppress Pomerode conversion to drift energy. They should suppress it because you can't ski anymore. So we should see all that smearing out of the above-threshold ionization spectrum. So we tried it way back in the old days when we first got our handle on some short pulses. And we did see, you could say it's kind of smearing out. Actually, it doesn't really look like smearing out. It looks like a lot of really sharp structure. Okay? Really, really sharp structure. In fact, if you're an old atomic spectroscopist like I am, it not only looks like a lot of really sharp structure, man, that looks like a Rydberg series if I ever saw one. That's just got to be a Rydberg series, right? It's got to be. So, a little mysterious. What's happening there is the role of, well, the Rydberg states, the role of the high-line intermediate states is beginning to come in to assist ionization. You're getting a little enhancement of the electrons that are produced up here or up here, because along the road they were in resonance, multi-photon resonance, with some bound state. And depending on how much AC start shift there was, they could be shifted into resonance for this red state, or for this sort of light-colored state, or for this dark blue state. And every one of those will make a different peak. The size of the peak will depend on the order of the multi-photon resonance, and also the intensity, which drives how fast how intense this multi-photon process is. And so really this is a form of spectroscopy. This is it sort of removes the idea that you have spatial and temporal averaging, and gives you those shells, those small tori inside your focus where you happen to be in resonance at that time for different states. Now, let's take another look at electron trajectories. The same picture I showed before. Now, you know that when the trajectory returns to the origin here, that means it's recolliding. And of course, that's what leads to high harmonics. That's what most of the real excitement is about these days, all those high harmonics. But also it can lead to rescattering. That is a different kind of a process, either elastic rescattering, which I'll talk about mostly, but even inelastic rescattering. That is, one channel is go back to the ground state, another channel is go to some excited state, a third channel is don't get any state, just scatter and stay in the continuum. All those things can happen. You can see, for example, at certain ionization times that you get a very, very low velocity returns. Other times you get higher velocity returns, and you can also get multiple returns. Those are really high velocity returns. Now, how should we understand this reapproach to the core? Well, a really cool idea, which I'm just going to touch on just so that you know it, is let's go into an accelerating reference frame. Since so much of our physics depends and scales as the wiggling motion of a free electron, let's just make that the origin of our coordinate system. We'll put the origin of our coordinate system on the locus of an oscillating electron. Well, I hate to tell you, but that is not an inertial reference frame. So what? What happens if you have non-inertial reference frame? Does physics stop? Oh, it does. You get fictitious forces. Well, I guess because we call them fictitious forces, maybe that sort of means that physics does stop. Anyway, you get fictitious forces, but you can see kinematic quantities in a new light. In a new light. That's my first pun on light. So, for example, let's take a look at these ionizations where we said that we had, by the way, there's a name for this. This is the Kramers-Henneberger frame. That's the oscillating frame. Let's take a look at this strong field ionization, where in our approximation, electrons start at zero velocity when they're ionized. Now, in the oscillating frame, zero velocity means that in a one dimension this way versus time plot, where I have oscillating coordinates, oscillating with the electric field, it means that the electrons are going to move in straight lines, but they're going to be ionized at a point where they are at the same place and time as an ion. The at-rest ion now looks like it's the one that's oscillating, but of course it's only its coordinate that's oscillating. It's not. And the point of contact here is a tangent, because they have the same velocity at the beginning, that is, they're at zero velocity. Okay? So it's every tangent. This is kind of cool. This means that I have a graphical construction now of the kinematics of strong field ionization. Well, let's take a look at it, see what we can learn. Okay. Here, for example, are three very closely spaced projectors. You know, these are the ones I showed you. 4 degrees, 8 degrees, right? We saw that a small change in phase made a big change in velocity. Well, now you see why. Are the drift velocities, that is with the wiggle taken out, of the electron. So an electron that has just wiggling and no drift would have to be the one that was made at the point where the tangent to the ion curve has 0 slope, right? That's right here where the electric field's at its peak. But that's exactly what we already knew. The electric field at its peak, you ionize there, the electron oscillates, but it doesn't drift. It moves back. Well, you see that. That's the 0 slope electron. Also, it comes exactly back and kisses the ion again 1 cycle later. Now, if it's made a little bit later, it will recollide. Of course, that's why you get high harmonics. But take a look at these recollisions. These are places where there's a very, very large difference in slope of the electron and the ion trajectory. Now, that difference in slope, that's the relative velocity of the electron when it comes back. You know, in the inertial frame, the ion's not moving at all. And all that velocity belongs to the electron. In this Kramers-Henneberger frame, they're both moving in our coordinate system, and they have different slopes. And it's the difference between those slopes that's that velocity. Okay? Now, think about rescattering. Think about elastic rescattering. Elastic rescattering is, you know, tennis ball off a wall rescattering. Okay? The wall is supermassive, just like our atoms. The electron's super light, just like our tennis ball. And all that happens in one dimension, for sure, all that happens is velocity reverses. Well, I already figured out what its relative velocity was. So if I square that, I can find out what its initial kinetic energy is in that field. Okay? And then it continues to move in the field, but with a different velocity. And the analysis of this very simple sort leads to a kind of an interesting revelation about how rescattered electrons are. Depending on where they rescatter, they can produce very, very high energy electrons, much higher than the 2 UP plus 1 UP offset that we saw for the directly ionized electrons. In fact, this plot here shows along the bottom here are all of the electrons that bounce off on their first return to the atom. If they miss that first time and they come back and bounce off on the second return, that's n equals 2. If they go to the third time, it's n equals 3, and so on. You see a lot of really cool stuff here. First of all, you see this really nice even odd thing, okay? Where it's the odd returns that make the high energy electrons. I think that's kind of cool. Also, the first return has the highest energy electrons. So we can really learn a lot about electrons. And so, by the way, if we start doing spectroscopy, we look up here at 10 UP, we'll be seeing those highest energy electrons. We'll also be seeing, according to the model, you could say we'll be testing the model. We'll be also testing the model to see what the physics is of the first rescatter. We look at the highest energy electron. Okay. Now, let's move along, because I wanted to, what time is it?
You have about half an hour.
6 minutes. You have about half an hour.
Oh, 10 past?
10 past 6.
Good. I'm on schedule. Let's get beyond single, oh, I misspelled electron. You see how sleepy I was? Let's get beyond single electron atoms. Very few single electron atoms in nature. Pretty much none of them come out of a bottle without doing something really special. What happens when you worry about the other electrons? Well, there are two main kinds of features that I want to concentrate on here. The first one is non-sequential multiple ionization. So you could imagine multiple electrons coming out for lots of reasons. After all, why don't we just go study that for a while? It seems like it's an extremely valid thing. Why is it like that? Let's take helium, for example. Both electrons have the same binding energy. They're in a degenerate 1s state. How come only one comes out? Interesting little dynamics question. Maybe we'll add a second question. Okay. Well, the answer to that question experimentally is that sometimes both of them do come out.
Yeah.
In fact, maybe it sounds a little paradoxical, but at the lower laser intensities, the probability that they both come out kind of in a concerted way, that is, they come out together, one coming out causes the other one to come out, however you want to talk about that, is actually quite high. And the reason that you know that that's true is because we have this beautiful agreement with either classical or ADK theory for ionization that we can compare to our actual ion yields. Now, I showed you that Steve Auk's paper from the old days where everything just matched absolutely beautiful. Well, along comes Lou DeMauro with his much more careful and patient approach, and he finds that, in fact, the ADK works really well for a single ionization of helium. The double ionization of helium, ADK would follow this inner curve here, inner part of this gray curve. So actually, if you get up to high laser intensity, above 10 petawatts per square centimeter, it kind of does follow ADK, but down here it sure doesn't. There's an extra process, a non-ADK process. And that's what Lou, maybe I'm not sure who coined it, but he probably was the person who coined it, might have been. That's what this so-called non-sequential ionization is all about. Now, it's been studied to death. It's been studied absolutely to death. In fact, it is no longer, I would say, a really hot topic for study, mostly, because it's been so much studied. And from all its characteristics, it looks like E2E inelastic scattering. It actually looks like it comes from those recollisions. It's one of the things recollisions can do. They can elastically scatter. They can also inelastically scatter. If they have enough energy, they can even ionize. And that seems to be contributing a lot to this population. Okay, something else that happens beyond single electron atoms, strong field ionization of inner orbitals directly. Not from rescattering, but directly. Okay? Now, this has been seen a lot in high harmonics. And I showed here some stuff from our own lab, but there's other people's labs who have done this, a lot of them. Paul has done it, for example. We've done it in other molecules. But the idea is that if you really look carefully at a high harmonics spectrum, so this is a high harmonic spectrum from a molecule, SO2, as you coherently move the rotational coordinates of the molecule around, I won't go into more detail than that, but just imagine I can look at this on this axis as rotating the molecule around in some certain funny way. This happens to be an asymmetric top, and so it's in a very weird way that it tumbles, but it still tumbles in some way that you can follow. You see that the high harmonic spectrum depends an awful lot on that instantaneous orientation. You can use that to match up different orbitals that might have been the ones contributing to the ionization and recombination. And when you do that, you find that actually it looks like it's pretty common for not the outer electron, but one of the other nearly outer but not really electrons, ones that are bound by a couple of EV, to participate and in fact dominate in high harmonic generation. Well, that's high harmonic generation. But, you know, if one electron manages to make a high harmonic, 999 contributed to the photoemission spectrum. So shouldn't we be able to see this in photoemission? Maybe. Maybe. There's some recent evidence of that. So now I've spoken about a number of different things. I haven't covered the entire universe of photoionization and strong fields. I've chosen some things that kind of fit together in this picture of above threshold ionization. And what we want to do now is kind of put it all together, because when you do an experiment, chances are you're not able to decide which of these things is happening. They're all happening. You know, you have to look at one or not. Okay. So here's a little simulation of putting it all together. This is just ionization of hydrogen, showing that the quantum mechanical wave shows evidence of rescattering. It shows all of the different dispersion of electrons coming out at different energies, at different angles, and different times. And we would like to do experiments that can capture that complexity. You know, not just these single narrow angle, let's look at the whole thing, okay? So we and many other people have adopted a kind of detector to do that called a velocity map imager. It's very simple. I'll explain it in a minute, but I just want to point out that it produces a momentum map or a velocity map. I don't know why it's not called a momentum map imager. Why is that?
Because momentum is real stuff.
Someone knows.
Because momentum is serious. Velocity is not serious.
Velocity, that's serious. These velocity map imagers produce these beautiful pictures. You know, every little wiggle here is real. I mean, some real physical phenomenon. These little spider legs coming out. And here, these are the Freeman resonances. Momentum increases away from the middle. And the polarization of the laser that was driving it is this way. So you can see most of the currents coming out here, but not all. You can see some rescattering way up there. There's a nice circle here, which turns out to be right at that 2UP place. Beautiful. It's all there. It's so easy to make, too. It's a two-dimensional imaging plate that you use electric fields to suck photoionizing electrons onto the plate. And so you get a kind of a pancaking of the momentum component that's along this direction, but in the transverse directions, it's true, it's accurate, it's good. It gives you that thing. It's great. So the scale of this is set by the wiggling electron free momentum. That's the wiggle. That's the momentum maximum that corresponds to the power mode energy maximum. And in fact, if I draw a little circle exactly at that point, it really does correspond to where the current drops off very dramatically in my spectrum. Now, let's start taking a look at some cool things. One of the things we were sort of interested in, other people too, is these electrons that come back and it seems like something that very often happens at these very low energy returns. Low energy returns are a big deal. And now we have a momentum map imager. We can look at low momenta pretty easily. We can blow this up as much as we want. So here's a blow up. This is argon. And this is just argon ionized in a Ti-sapphire laser field. There's absolutely nothing special. This is totally generic now. Okay? All we did is look really close at the very low momentum. And well inside the first ATI peak, you see other structures. And by now, at this point in the talk, you look at that structure, you heard about the Freeman resonance, and you say, man, if that isn't a Rydberg series, I don't know what it is. That's a Rydberg series. What is that? That's not an ATI peak. It's well inside. We're looking at really low momentum here. What is that? What that turns out to be are auto-ionizing states that are caused by something that we always did know could happen. That is photoionization, not to the ground state of the ion, but to the first excited state. The first excited state of a rare gas cation is the fine structure split state. Linda has studied this in X-rays. A lot of people have studied this, but not this auto-ionizing feature from strong fields. This is kind of new. And it's so distinct. In fact, what's interesting about it is that the width of these lines is so small. Here's EV. The width of this is 0.005 UV. That's less than the transform limited energy width of the laser that did the ionizing. But of course, that's not surprising because it's an auto-ionizing state. It's actually debris that's left over and hangs around for microseconds and then decays. or at least hundreds of nanoseconds. And that's what's causing those very narrow features. Okay, great. See something simple. Oh, by the way, here's in krypton, and it's just incredibly gorgeous in krypton. You can see the same thing. Auto-ionizing rings. We saw it in Argon first, spent a lot of time on that. Then went to krypton and were just blown away. Okay. Well, this gives us a way of studying the excitation process. The excitation process itself is pretty fast. It's field ionization. It's this thing it's an attoscience topic. We're not doing attosecond pulses, but the approach to excite these states as all of the Pondermotive shifting and everything is going on in the system is something that could give you access to attosecond timescales. There's a way to probe attosecond time. Now, a fundamental feature is that different drift energies ionize at different times. That was one of the first things I mentioned. Now I want to come back to it, just to remind you that's these slope differences here correspond to very slightly different time differences. So with this velocity map imaging thing, can we tell anything about that? Can we actually measure it? In fact, as successful as this model is, I would say most of us experts, whatever we call them, people like Ken Schaefer, I mean, most of us are going to kind of doubt the validity of this idea that different electrons ionized at different times have different energies. Just because it works for recombination and atom chirp and all that doesn't mean it has much to do with what's going on up here. Why? Well, because it's really tunneling, and you're asking the wrong question. It's not when, it's at what rate does, stuff like that, right? Okay, fine. Let's just look at an experiment. We can extract the dynamics by modulating the field with a second laser. So we add a second field at let's see, I have to say this right. Look at this picture. We strong field ionize our system. That's this blue curve, oscillating electric field, right? And then we add a very, very weak half frequency field. And the idea, of course, is to make it so that sometimes that will constructively interfere with this electric field and make these peaks bigger while this one is smaller, that kind of thing. So it's a way of tweaking that phase a little bit, just tweaking the phase. This was our idea. That's why we were doing it. Okay? When you do that, this is what that VMI picture looks like. This is a truly tiny field. We're talking about something that is maybe the intensity of this beam is well under 1% of the intensity in the main beam. It means that the field is a few percent, less than 10%. Has a gigantic, super gigantic effect on which directions the electrons go and also on a lot of other stuff. If you want to think about this small field as being a little perturber, then on top of all this multiphoton ionization, you have a little single photon at half the frequency that can either promote an electron to higher energy or demote an electron to lower energy, and so you have two-path interference of those two processes. That's a way to kind of motivate your thinking about it. Of course, that's terribly oversimplified. That's terribly oversimplified. But nonetheless, there's some truth in it. Okay, here's the data again. This is shown in a slightly different view. And what we've done is taken this apart by integrating over this half circle and ask when does the current come out here, and integrating over this half circle ask when does the current come out here. And we can plot those as a function of time, and we see that these different ATI peaks and these little sidepan peaks in between that come and go with phase all have different times, different phases when they add up. So now you begin to see the method here. We're really trying to find out if the low energy ATI peaks have a different phase offset from the high energy ATI peaks because they're produced at a different time, is the idea. really what we're measuring here is something that is called in the business of Wigner delay. The idea of the Wigner delay is shown in this little animation. I wonder if it's going to repeat. Probably not. Okay. The idea is that when you ionize in the strong field approximation, you don't worry about the Coulomb field that is pulling back the electron. And of course, the Coulomb field is a big deal. It causes a change in the time that an electron gets to you. That if it has a certain energy, it becomes potential dependent. A free electron, actually, it's a little paradoxical, but this picture made it very clear. A free electron gets out slower than a bound electron. You might think a bound electron is going to get out slower. But no, what we're doing is comparing two electrons that have the same final energy. So then the bound electron gets here faster. All right, fine. So we plot that. All we're doing is plotting where these peaks are as a function of ATIP. And what we find is that the even and odd peaks are pi separate. That's actually what we expected. This is a strong field approximation result. But there is a very, very strong intensity-dependent effect for the low energy peaks. Okay? And this is a real view. It's not what I would call a transparent view, because you have to deconvolve the entire process of ionization. But this really is showing you that distortion of the Coulomb potential, the intensity dependence, the fact that this curve doesn't look like this curve, when all I did was cut the intensity by 4. It shows the effect of the distortion of the Coulomb potential. So our idea is that we're going to kind of play around with this now and see if we can use this to understand the physics of field ionization. Okay. Finally, I'm going to end up with something, because Lou tomorrow is going to talk about laser-induced electron diffraction. And it's really just a couple of slides. I know it's late. But remember, now you've got a pretty good picture in your head of what these velocity map images look like. And I've shown you krypton, and I've shown you argon, and I have steadfastly avoided showing you a molecule, and now I am. I'm showing you molecules of nitrogen. Everything else is the same, 800 nanometers. It's all about the same. And it kind of looks the same at first. It has this circle, but has something else as well. It has these two other circles. It has one up here, and it has one down here. And, see, I'll show you that again. You can see them by eye. Okay? And the notion that Lou, and also we, are now following up is that this is caused by not just attosecond rescattering, which happens in the atom too, but attosecond rescattering from a molecular potential, which produces molecular diffraction. In addition to atomic rescattering, you now have diffraction. Some momenta would like to scatter more than others. He wrote a Nature paper on this in 2012 and got us all excited. Here's something from that paper, the Blaga paper, that shows the physics of what's going on. Let me go back to this picture first. That this circle is a scattering ring. I'll show you in a minute that it really is. A scattering ring happens when you take a quantum mechanical projectile like an electron and send it through a gas that has some non-trivial potential, like a molecule that has multiple atoms in a particular relationship to each other. They'll diffract the electron more efficiently into certain angles because of constructive interference between the different centers. Now, the weird thing in the strong field case is that it seems like if I have a beam of electrons, I should see that scattering ring here, right centered on zero momentum. It's an equal momentum in all directions. But instead, I saw it up here and down here. And this is really what Demaro and Blaga explained. They pointed out that it's because that rescattered electron is still in the laser field. The same thing that makes the 10 UP happen, because when you rescattered, you were still in the laser field, and you had to accelerate more in the laser field, right? That same phenomena shifts all scattering off of the molecule, either ionization or rescattering, by 2UP, or in momentum, by A naught, by the vector potential, the peak vector potential. And so there's that circle around the peak vector potential. He was doing this with infrared, and there are different things that are different from our experiment. But he points out, for the first time, I thought, that centered right on here is where you should see the scattering rings. And of course, since it's linearly polarized, centered also here, you should also see scattering rings. And so that's really what we were doing. Now, we've been playing around with this. One of the cool things is that we can align nitrogen molecules. We know how to do this, everybody else does too. Well, those scattering rings are much more prominent when the molecules align with the polarization known as anti-aligned. That's an interesting fact. We've also, we've taken a look at these beautiful pictures. We said, if I really care about this ring, there's got to be a way of getting rid of all of this. One man's signal is another man's background, So there must be a way of getting rid of all this other stuff by finding the correct basis set to project my electron patterns on. I want to know about patterns that are centered here. I don't care about patterns that are centered here. So I should do some kind of a Legendre polynomial decomposition, a projection of my data. You guys are theorists. I'm sure you immediately get the idea. You can find a basis where the information you want is sparse in that basis, and that's your basis. So actually, we've done that. So if you do that, this ends up being that scattering ring from nitrogen. And I challenge you to compare that to anybody's electron beam experiment. I mean, these things are as good. Well, there are some caveats here. It happens in a strong field. It has to be a molecule that you can do that with. But you make beautiful patterns. So we're now trying to explain this. Okay, I'm done. So most of the electrons in strong field ionization never make high harmonics. That's the first take-home message. The second one is that their spectra reveal the dynamics of the strong field laser atom interaction. You look at their spectrum closely. The more you look, the more interesting subtleties you can find out about that interaction. And now that we've extended it to molecules, we may even also have new methods to probe structure and dynamics on this attosecond angstrom timescale that so much of the workshop is devoted to. Thanks very much, and I'm really happy to get a discussion now or at the close.
Thank you, Phil. Questions?
In your last slide, how did you get it so clean? I'm not clear how you removed.
I thought the theorists would pick up on this right away.
Legendre filter.
It's a Legendre filter. So what you do, typical Legendre filter, which we use all the time, a lot of people use it, is that you end up with a VMI image that's all kind of speckly. But those speckles, those are just Poisson fluctuations of particles hitting. What you care about is the pattern that you would see if you collected an infinite number of electrons, right? All those speckles and the Poisson fluctuations got small compared to the signal. So one way you can cheat to get there faster is to project your data onto a basis of Legendre functions for each radius. So you divide this into lots of little radii, lots, like hundreds of little radii. And at each radius, you have some signal. You project that onto Legendre functions, P0, P1, P2, P3, up to P10, up to P50. At some point, you cut it off. You'll be able to see where it gets cut off. There's actually a nice knee. And then all that other stuff is noise. And so then you just plot it, and you just plot the Legendre coefficients rather than the individual little speckles.
Why don't you see two rings? Because
You do see two rings. I just showed one. If that's the question. We just blew up this area right here. There are two.
So that's the left-hand side.
Yes.
Lars.
I have a question regarding your orthogonizing signal. You have this signal at low energy from a process where you have a decay to an excited state in the atom, right?
Oh, you mean the low momentum?
Yeah, the low
Yes.
momentum, the low energy electrons
Right.
emerging from the...
Those are very, very low energy electrons. So what happens is that, we did a couple of experiments back in the 80s that spoke exactly to this problem. If you can do above threshold ionization, for sure, you're also trapping some population in bound states. Now, the population that is most readily trapped is population that has bound state Kepler orbit times that are longer than your laser